In this lecture, we will be examining methods for analyzing the relationship between two variables and sample selection. This covers chapters 6 and 7 of your course textbook. A simple linear regression can be conducted when you want to find the relationship between two quantitative variables. It fits a straight line through the set of data points so that the sum of squared residuals are as small as possible. This is a fancy way of saying you want your data points to be as close to that best fit line as possible. In this lecture, I'm going to be discussing what a simple linear regression tests, and also differentiating this from a correlation, where you calculate an R-squared value. An example of a simple linear regression might be assessing the association between the number of units packaged and time. You would expect to see the number of units packaged to increase as time increases. But first, let me explain residuals. A best fit line is developed by minimizing residuals. Residuals are the difference in distance between the line and the data point. This is done iteratively, so that all the data points are as close as possible to the best fit line. In the figure, there are 3 data points. A best fit line is placed so that the distance between the line and each data point is minimized. This is done so that the data points are as close to the line as possible, given the relational distance each point is to the best fit line. These residuals, however, should carry certain characteristics in order for the linear regression to work properly. First, if you plot the residuals, you would expect to see them have a constant variance, with a mean of 0 and normally distributed. The constant variance can be visualized. If you see a pattern that looks like a funnel set on its side, this would be a sign that the residuals do not have constant variance. Also, we can plot the mean in order to determine if it is 0. The best fit line can be explained with an equation. Many of you may remember this from your algebra courses, where the equation of a line is y equals a plus bx, with a being the y-intercept and bx is the slope. The linear regression actually assesses if the best fit line is significantly different from 0. If the line is flat, the p-value would most likely be quite high, and you would not achieve significance. However, a line could deviate slightly from being flat and achieve significance. Therefore, the p-value for the linear regression does not tell you about the strength of the relationship between the x and y variables. An R-squared value does just that. As such, it assesses the proportions of the observed values of y explained by the linear regression of y on x. As an R-squared value approaches 1, this indicates a stronger association between the x and y variables. It is not uncommon to have a significant linear regression where the p-value is less than 0.05, but the R-squared value is weak. This would indicate that there is a significantly weak association between x and y. In some cases, such a relationship is meaningless. Therefore, interpret the simple linear regression with caution. The hypotheses for the simple linear regression is based off of the slope of the line. The null would be beta is equal to 0, or the slope is equal to 0. The alternative hypothesis is that the slope is not equal to 0, or beta is not equal to 0. There's no directionality indicated for the linear regression. A positive association, one in which the line ascends, and a negative association, one in which the line descends, is handled the same way. After the hypotheses are defined, the t-stat can be calculated to determine the p-value given the degrees of freedom. Finally, you can state your conclusions. The conclusion may be the following. There is enough evidence to reject the null hypothesis, which suggests that there is an association between the x and y variables. It is always wise to include the R-squared value as well, so others can understand the strength of the relationship, either as weak, moderate, or strong. Let's look at an example. Let's say we want to determine if there is a relationship between the number of medications and a measurement of quality of life. Looking at the plot below, we see that the data was drawn on a scatter plot. Each point on that plot is for a single observation or a single person. Therefore, if you focus on just one dot and follow that dot down to the x-axis, this would indicate the number of medications for that person. With that same dot, follow a line to the y-axis. This would indicate the quality of life score. If we were to draw a best fit line through the center of all these points, we could see that the best fit line is descending. This indicates a negative association. We still don't know, however, if that association is significant. A linear regression would determine if the slope of that best fit line is significantly different from 0. The null hypothesis would be that the slope of the best fit line for the association between quality of life and number of medications is equal to 0. The alternative hypothesis would be that the slope of the best fit line is not equal to 0. If we run the linear regression and obtain a p-value less than our alpha of 0.05, we have enough evidence to reject the null hypothesis and conclude that there is a significant negative association between quality of life and number of medications. Therefore, as the number of medications increase, the quality of life scores tend to decrease. If we try to understand the strength of this relationship, an R-squared value is required. The R-squared value is based on the distance at the points R from the best fit line. Because each point is relatively close to the best fit line, it's likely we would see an R-squared value closer to 1, indicating a stronger negative relationship. In this example, we are looking to determine if there is a relationship between the length of stay and age. We see that as age increases, the length of stay tends to increase. This would indicate a positive relationship. We can test if the relationship is significant with the linear regression to determine if the slope of the best fit line is significantly different from 0. We might find that the p-value is less than our alpha of 0.05, indicating a significant positive association. However, the points aren't very close to that best fit line, so when we look at the R-squared value, the value is likely to be closer to 0, indicating a significantly weak positive association between length of stay and age. In this example, we are testing if there is a relationship between years of experience and error rates. We see that the points are pretty scattered relative to the best fit line, and the line appears to be rather flat. The linear regression will likely reveal a non-significant result where the p-value is greater than our alpha of 0.05. This would tell us that the slope of the best fit line is not significantly different from 0. Therefore, there is not a significant relationship between error rates and years of experience. Given that the relationship is not significant, there's no need to test the R-squared value. But if we did, the value would likely be close to 0, given that the points are not very close to the best fit line. When working with a linear regression, here are some hints to be aware of. Use a simple linear regression when you want to determine if there is a relationship between two quantitative variables. The p-value of the linear regression only tells you if the line is significantly different from 0, whereas the R-squared value tells you about the strength of the relationship between the two variables. Let's now shift gears and discuss methods of sample selection. Sampling is often employed to minimize bias within data so that you are certain the sample of data you are working with is representative of the desired population, and any analyses will have meaning that can be generalized. To begin, let's get some terminology out of the way. A sample is simply a subset of a population or universe. We use a sample that is representative of the population because it is often too difficult or unfeasible to study a complete population. There's only one instance when you are evaluating a complete population, and that is with a census. A universe is a set of all units that are eligible to be sampled, yet typically unattainable due to resource limitations. For instance, it would take a lot of time and money to conduct a study on every person in the United States with hypertension. A sampling frame is a listing of all the subjects in the universe. For example, this may include patients, physicians, or health records. A sampling plan is the definitions of the population and the inclusion or exclusion criteria you intend to use for sampling, and the sampling method. There are two primary sampling methods. The first is probability sampling, where each member of a population has a known probability of being selected for the sample. For example, it's random. Specific techniques of probability sampling include simple random sampling, systematic random sampling, stratified random sampling, and cluster random sampling. In non-probability sampling, members of a sample are deliberately selected for a specific purpose. For example, it's not random. Specific techniques of non-probability sampling include convenience sampling, judgment sampling, and quota sampling. I will discuss each of these techniques in more detail in the subsequent slides. Simple random sampling is arguably the most popular sampling technique. With simple random sampling, every member of the population has an equal chance of being selected for the sample. The technique is equivalent to pulling names out of a hat. A systematic random sampling is a simple random sampling method, whereas the selection process is a bit more detailed, where you choose to include every nth member in the sample. For instance, you might have a random number of names, and you choose to include every fifth name in the sample. The order of the names must be random. They cannot be alphabetized or sorted in any particular way. This is a useful way of sampling when you're unable to carry out sampling with the help of software. Stratified sampling is a method where a population is divided into smaller, non-overlapping groups or strata based on some specific criteria. Once the strata are split up, a simple random sampling method is carried out. For instance, you might split males and females into separate strata and select 20 males and 20 females from the respective strata using a simple random sampling process. Cluster random sampling is a process where a population is divided into exclusive and exhaustive groups based on this, before the sample is selected. That is, every unit in the population is assigned to one and only one cluster. Clustering can be a multi-stage process. In one-stage cluster sampling, clusters are selected at random and all units in that cluster are included in the sample. An example of a one-stage cluster sampling is to randomly select a day in the month and select all, I repeat, all cases that are coded on that day in the sample. For two-stage cluster sampling, the clusters are selected at random, and the units within the randomly selected clusters are selected at random. For example, if we were to randomly select 3 shifts occurring during the month, and then randomly select records from those 3 selected shifts to make up the sample, we would be carrying out a two-stage cluster random sampling. Next, we will look at non-probability sampling. The first technique is convenience sampling. With convenience sampling, you essentially create a sample based on who you are able to solicit or based on who volunteers. The problem with convenience sampling is that you're often left with a biased sample that isn't representative of the target population. Judgment sampling, another non-probability sampling technique, is completed by a researcher with expert knowledge of the subject matter, and choices for sampling are based on that person's knowledge. Data analysts will use judgment sampling when they evaluate data and select records or entries that require further investigation based on their expertise. Quota sampling segments the population into mutually exclusive groups, as done with stratified random sampling, but then judgment or convenience sampling is used to select a number of individuals for the sample. For example, you may choose to segment the population into male and female physicians, and ask the first 5 male physicians and first 5 female physicians you see to participate in your study. This would be an example of using quota sampling with convenience sampling. In closing, a simple linear regression can be used to test the relationship between 2 quantitative variables. Sampling is an important method for minimizing bias in data. There are numerous sampling methods that can be employed. It's important to really understand these options that are available so the best method can be utilized.